This lecture will focus on mechanics, units, numerical calculation, and a general procedure for analysis. And if you're looking at the slides on Brightspace, what you'll notice is that there are some slides that I don't cover in the lecture set. You'll notice that the example problems I take are not from the lecture slides, although there are example problems that are worked in the lecture slides. I do that on purpose. I do that so that you have other sources of examples to hopefully study and learn even more. So today, after today, actually, you should be able to explain mechanics and statics, what it is, work with two types of units, and round a final answer appropriately, not an intermediate answer, but a final answer, and apply some problem-solving strategies. Now, there's usually several in-class activities that I would go through in a normal semester, but this being not a normal session since you're watching the video, the quizzes are in the course learning site, but some of these things we simply will not cover. So what is mechanics? Well, it's a study of what happens to a thing, an object, a body is the technical name, when forces are applied to it, to that body. Now, the body can be large, the body can be small. The forces can be large, the forces can be small. In my design experience as an engineer, most of what I dealt with were relatively small force things. I designed, the smallest machine I ever designed was about 1 inch square. It was a little press for pressing together a little crimp connection for an electrical circuit. But the machine, whatever it is, whatever the body is, can be large or small. If you've ever looked at a rail car, it's a relatively large force. Relative to what? Well, relative to a penny sitting on the track. The penny is going to be squashed, obviously. On the other hand, the rail car is a very small body by comparison to Earth. So it just depends. So the bodies can be large, they can be small. The forces can be large, can be very small. An interesting thing about force, though, is that most of the time, force is more something that we make up. If you say rest your hand on a table and lean on your arm on that table, you can imagine how there's pressure on the entire surface of your hand where you're putting your hand against a table. And that pressure will vary. For example, the pressure out on your fingertips won't be as high as the pressure on the palm of your hand. But all of those, that pressure distribution integrated over your hand or added up over the surface of your hand add to a force in a particular direction. And so a lot of times forces are actually distributed pressures that get added up, if that makes sense. And one thing that really confuses students is students often think that you have to have some effort to apply force, that effort is force, that, you've helped your friend move and you've pushed a box along the ground because you got tired of carrying them out to the U-Haul van, and you think, well, this is a lot of work, this is hard, so to apply force to lift this box, well, to lift the box, yeah, to change its position in the gravity field, that does require work, but actually, to apply force doesn't require any work. Think about it this way. You could get tired, set the box down, and sit on top of the box. What are you doing? You're applying force. How? By the weight of your body, right? Your body's own weight is applied to the box, and yet it requires no effort on your part. So be careful thinking that force requires some effort because you're used to, if you push on a wall and you can't push it, you can still apply a lot of force and you can really try to push the wall and your muscles are straining. Of course, the wall doesn't go anywhere unless it's a poorly built wall. But we get this idea in our day-to-day life that force requires effort, and that's not actually the case. There are many things where force can be applied without your effort or the ground's effort. For example, if you stand up on the ground, on the floor, wherever you are, you should realize that you are applying force to the ground. Why? Well, because you have weight, right? The earth is pulling on you, and if you think about it, you're pulling on the earth. You might think for a minute about how much force the earth applies to you versus how much force you apply to the earth. You might think, well, I don't apply near as much force to the earth as the earth applies to me because, hey, after all, I'm a lot smaller. But actually, you are pulling on the earth with your body's mass just as much as the mass of the earth is pulling on your body. They're equal and opposite forces. And that's why you're not falling through the floor or flying up into the sky, because the reaction force, the force from the floor onto your feet, is equal to the force that your weight is applying through your feet to the ground. You can think about this by imagine a bathroom scale where you set it up normally and stand on the scale and you can read your weight. Fine. What if you turn the scale upside down? Then what? Well, what are you doing? Are you reading the Earth's weight? Yeah, actually. The Earth's weight. How much does the Earth weigh? Well, it depends. It depends on what body is attracting it, right? The Earth's weight versus the sun, when the sun is attracting it, is a totally different thing from the Earth's weight from your body attracting the Earth, or a backhoe attracting the Earth, right? Now, the mass of the Earth, that's a different thing, but the weight of the Earth, weight is a force, whereas mass is an amount of matter, if you will. Now, sometimes what we'll do, if you look at the figure on the left, you notice there's a couple of chains going down to some large casting. It looks like it's been machined. A lot of times we're interested in force at a particular point, and so you might notice that, sure, there's force in the two chains that go down at an angle, but mainly what we're interested in is the force in the single chain going up, or the force at the hook. And so we're always interested in forces applied to points, when in reality, most of the time forces are not really applied to points. If you think about the rail wheel there versus the railroad way, you'll realize that if you were to apply all of the force to a single point, so it's a curved wheel, if you apply all the force to a point, that's a whole lot of force over a very small area, and that means a very large pressure, right? Because pressure is just force over area. And so what would happen is actually the bottom of the wheel, where it's curved, it would have to go flat, at least somewhat flat. As a matter of fact, that's exactly what happens. The contact between the wheel and the rail is not a single line or a single point. It is, in fact, an area. The wheel literally flattens out a little bit. The rail actually dips down just a bit. Now, within the elastic limit, which we'll talk about in another class, in other words, it acts like a spring and it can spring back. It's not permanently deformed. But, in fact, the wheel does deflect. Anyway, we're not interested in all that. What we're interested in is the net effect of all that pressure, it all added up, and what the net force is at a particular point. There are several branches of mechanics. We've already alluded to another. And what we're studying right now is rigid bodies, things that cannot change shape at all. And in that, we've got statics, which is the class you're in, and then dynamics. What's the difference between the two? Well, statics is all about bodies where the force is balanced. In other words, if the body's already in motion, it remains in motion at exactly the same speed relative to some reference. Whereas if the body changes its speed, well, then that's dynamics. That's a different class. And so things like buildings are certainly static structures. Well, okay, buildings are ideally static structures. In reality, when they're falling down, they are dynamic. Hopefully you're not in one when it falls down. Anyway, so dynamics, though, are like you get in your car and you push the gas pedal and your car goes from 10 miles an hour to 20 miles an hour. It has accelerated. You've changed its speed relative to the Earth, and therefore it has accelerated. Its velocity's changed. That's the same thing, okay, except acceleration is just velocity change over time. That's dynamics. We're not studying that. So in this class, all forces will balance out. I know it sounds sort of like Star Wars and, the force is in balance, but that's not really what we're talking about. We're talking about mechanical forces applied to a body being in balance such that the body does not accelerate. Now, in reality, bodies are deformable. We've already talked a little bit about this with the train wheel. They do change shape. Sometimes they change shape like a spring and they come right back once the load is removed. Sometimes they don't. Sometimes the material that the body is made of deforms so-called plastically instead of elastically, and some of the change of shape is permanent. Another branch of mechanics is fluids, and that breaks up into incompressible and compressible fluids. You'll study that in other classes as well. We may do a little bit of work with fluids in this class, but primarily we're interested in rigid bodies, things that do not change shape, and in particular, bodies that are static and do not accelerate. In other words, do not change their velocity. Now, units are something that I harp on in all of my classes. You'll get tired of hearing me talk about it in the lecture and in the examples, but it's good for you. You really need to learn how to use units. You need to master units. So what do I mean? Well, I mean measurement. A large reason that our society is as it is today, and we don't live in, some hut out somewhere built by our own hands. We've got all these computers and videos and internet and, your cell phone and the clothes you wear. All these things are in large part due to the fact that we learn how to measure things, and we learn how to measure them better and better and better and better to the point that we know a lot about things and about how they work because of such precise measurement capability. So the units of measurement are absolutely important and critical because measurement itself is important. So there are fundamental things, quantities, or dimensions that exist whether we measure them or not. They just are. For example, length, right? The length of my house or my office or wherever you are, it is whatever it is, whether you know how big it is or not. Length is something that you can traverse through, right? You can walk down a hallway, for example. You could jump up in that dimension. You could walk side to side. There are 3 different dimensions of space that we live in: height, width, and depth, of course. But then other things exist, such as mass. Mass and length are not the same thing. We call mass a dimension. And people in their general language get confused between length and dimension. They think that a dimension means just length, but that's not true. We more generally talk about dimensions as other things that we can measure that exist whether we measure them or not, like mass. How much mass an object consists of is absolutely critical. For example, if you want to know how much force is required in order to support a certain mass, well, you better know how much mass there is, right? Because the more mass there is, the harder Earth is going to pull down on it. So if you think about a ship going into dry dock, well, you better know the mass of that ship so you can figure out, how much support structure is required to support the weight of that mass. Okay, time and force are similarly dimensions where we can measure magnitudes of physical quantities that simply exist. Now, Newton's second law relates some of these things. It relates force to mass and acceleration. Of course, in this particular class, we won't deal with acceleration, but these dimensions are related to one another. As a matter of fact, acceleration is actually length per time per time. It's velocity, it's the change in velocity over time. And so force, mass, length, and time are all related to one another by Newton's second law. We will use this equation in order to develop a system of units. And units are just arbitrary names we give to physical quantities. That's all they really are. They're arbitrary amounts. We can make them whatever we want them to be. And of course, it's helpful if we all agree on how much a physical quantity is, a unit is of something, so that we can be reasonable in our dealings with these things. So unit systems. So I've already shown you how force, mass, length, and time are related by Newton's second law. Now, if you look at force, mass, time, and acceleration, leaving off length, you'll realize that 3 of these are SI units. In other words, they're base units. They're more basic things, whereas acceleration is actually made of something else. It's called a derived unit. Now, the one that's derived just depends on which system of units you use. And of course, we've got 2 primary units in this country. We've got metric and the standard or U.S. customary system. We will use both. And students seem to come in a variety of flavors, really 2. One group that thinks, we ought to use SI. There's no reason. Those are real engineering units. And other students who think, well, we should use only English units because, after all, those are what I'm used to. I disagree with both camps. I think we should use both because I really am glad we have both. I think it forces you, as you learn, to begin to think about the dimension itself and less about how much of that dimension we give a name to. So there are confusions that can occur because the 2 systems are different and the amounts are different, and you probably feel more comfortable with English units than you do SI. But as you go through your career and learn about these things and use units, I think your familiarity with SI will increase. And of course, both are used in the real world every day. You need both. So why not learn both? It's not all that difficult once you understand what's going on. 1 kilogram of mass is not a kilogram of weight. Let's be very careful here. A kilogram of mass will weigh 9.81 newtons when on Earth. If you take that 1 kilogram to the moon, it will weigh something totally different. In other words, the moon will pull on that mass with a different amount of force than the Earth pulls on it. In fact, the Earth will still be pulling on that mass. However, it's so far away, it won't be pulling as hard, you see, as it would if that mass was sitting on the Earth's surface. A slug of mass will weigh 32.2 pounds force. Now be careful. In the English unit system, we have a couple of different pounds to deal with. One is pounds mass and the other is pounds force. If you see simply LB, or you go to your bathroom scale and you stand on it to see how much you weigh, you are measuring weight or force in pounds force, okay? However, pounds mass are not force. Pounds mass are a unit of mass, just as a slug or a kilogram is. In the same way, unfortunately, if you go to your bathroom scale and you set its units to SI or metric, and you step on it, it will give you your weight in kilograms. Well, guess what? It's not. It's measuring your weight, but what it's giving you is your mass, and it's making a huge, well, maybe not a huge assumption, but it's making an assumption. That assumption is that your scale is on Earth. Today, that's not such a big assumption, is it? Whereas in the future, perhaps it will be. If you take that same scale to the moon and you stand on that scale on the moon, it will tell you the wrong mass that makes up your body. Why? Because it will assume that you're using the acceleration of gravity on Earth. In fact, it would be the acceleration of gravity on the moon. So there are two systems. We will use both. And one really important note, on exams and in homework problems and all the work you do not switch units. If I give you both metric and English, use whichever one you want. But if I give you metric, stick with metric, do everything with metric in that problem. If I give you English, do everything in English units, okay? I want you to master both. That is very important to me and is important to you for the sake of your career as well. Now, there is a summary in the textbook, and it goes as follows. It shows you international units and the standard length for that unit system, which is, of course, the meter. Now, both English and metric share units of time. A second is a second, whether it's metric or English, and so is an hour and a minute and so forth. But the standard U.S. customary FPS, or foot, pound, and second system, uses the units of feet for the dimension of length. Okay, notice I was very careful how I said that. I said the unit, which is the foot, and the dimension, which is the length. In the same way, a second is a unit of time. Okay, time is the dimension in that case. Mass can be measured in kilograms. That's the standard unit of measure of mass in the SI system, whereas the standard in U.S. customary units is the slug. However, you'll notice I use pounds mass more than anything in the U.S. customary system. And that's probably because of my chemical engineering background. The standard unit of force in the metric system is the Newton, but metric kind of nice because units often, when they can be broken down, they can be broken down into a nice set of units. So, for example, a Newton is a kilogram times a meter per second squared. That's what a Newton is, okay? 1 kilogram times 1 meter divided by a second divided by a second. That's what a Newton is. Whereas a pound in English units, a pound force, if you want to figure out how many pounds mass it is, it's a little confusing. It turns out it's a one-to-one relationship, but that doesn't mean that 10 pounds mass will always weigh 10 pounds force unless you're on Earth. You might say, well, I'll always be on Earth. Well, maybe, yeah, that's true. But I want you to have an understanding of the difference between a mass and a force, okay, or a weight. They're very different things. A weight is just the effect of two bodies pulling on one another, where those two bodies have mass. There are some very common conversion factors. They are in your book as well. They're repeated here for completeness, so we can talk about them. You will occasionally need to convert between the systems, but unless I've told you otherwise, work problems in the units that I give you. In fact, fair warning, Word to the wise is sufficient. If you work an exam problem and I give you metric and you convert to English, you will immediately lose 5 points on that problem. And each problem is only worth 25 points on average. So you're really shooting yourself in the foot and losing a fifth of the credit for that problem. If you say, oh, I don't feel comfortable in SI, so I'm going to switch to English. Well, okay, lose points. Don't do that. I'm trying to train you. I'm trying to help you learn both systems. Just bite the bullet and learn both. It's really not that bad once you kind of wrap your head around it. Conversely, if I give you the other unit system, do not switch from it as well. Work problems in the units that I give you. Okay. Could you convert a force of 47 pounds force into SI units? I would suggest you try this. There's the answer. Hopefully you came up with it. There are some conventions with the International System of Units that we use. We do not use plurals. For example, if a mass is 5 kilograms, we do not write 5 kgs, we write 5 kg, 5 kilogram. And we might read it as 5 kilograms, but we don't tack that extra S onto the end of the units. We separate units with a dot, so a meter times a second is a meter dot, or is an m dot s. Now, you'll see me use dashes instead. That does not mean subtraction. You can't subtract one dimension from another. That doesn't work. We're talking about multiplication or division of units, okay? And sometimes you'll see me just drop the dot between two units and just hope you understand we're talking about meters times seconds. Although I try not to do that because there are also Greek prefixes, and that could be confusing because m as a Greek prefix means milli, 10 to the negative third. So do I mean milliseconds or meters times seconds? Sometimes you can tell from the context of the problem, sometimes you can't. So a lot of times I will try to include a dash or a dot between units. Most symbols are in lowercase. There are exceptions. Newtons, pascals, which is a unit of pressure, begins with P. Mega and giga are certainly things that are not lowercase. You'll kind of see this as we go through example problems and see how to use it. It's a lot like learning a language, and there's always exceptions in every language. Exponential powers apply to units. So if you have 2 feet and you square it, not only do you have to square the 2, but you have to square the feet. So 2 feet times 2 feet is 4 square feet. Feet times feet is feet squared, or square feet. So be very careful about that with your exponents. If you square the number, you better square the unit as well. You should not use compound prefixes, and I've got some examples of that. And there is a table in the book to show you prefixes used in the SI system. So here are some prefixes. Giga is 10 to the 9th, mega is 10 to the 6th, kilo is 10 to the 3rd. You'll get used to these. They're not difficult. Notice that they move on, thousands. So one's 1,000, and the next is 1,000 times 1,000, then 1,000 times 1,000 times 1,000. Or the other way, dividing by 1,000. So 0.001 is 10 to the negative third. It's milli is the prefix used for that, and then micro, and then nano. If you're curious after that, it's pico, and then femto, I think. I don't remember. Anyway, so you'll get used to the prefixes as well. They're not too bad once you use them. Just remember they move by powers of, 10 to the third, okay? Now, we have to have dimensional homogeneity. In other words, you've got to have the same dimension on both sides of an equation. You can't have an equal sign and have one unit on one side and a different unit on the other. The two things can't be equal if they have different units. So if you come to a point where you think that your left and right-hand side of your equation should have different units, you've made a mistake somewhere along the way. In fact, units are very useful for helping you determine when you've made a mistake or detecting when you've made a mistake in your calculation. So you should carry units through. I don't always. I try to in my examples. Sometimes I get tired of writing the units, and as long as I know everything's consistent, then I might drop them temporarily. But you should not drop your units until you've mastered it. Another thing that's really important is to use an appropriate number for or of significant figures for intermediate calculations as well as your final answer. And what I usually do is I'll try to keep numbers in my calculator. So it's a whole bunch of numbers. And I don't get a lot of round off error. So you have to be really careful because, if you continuously round off in multiple steps, you can get farther and farther away from an accurate, precise answer. So definitely carry a good number of significant figures through in your calculations and then round appropriately at the end. Now, be consistent when you're rounding off. If you got something greater than 5, then you round up. If it's smaller than 5, you round down. You should know these rules from grade school. And if you have, a 5 itself, see your textbook for an explanation of what to do in that case. Now let's talk about a problem-solving strategy. And by the way, one of the reasons that I give you solutions to the homework in video format is because I know you can probably go to Chegg or some other place online and find the solution to every problem I give you, except for the ones that I write for your exams. And of course, during exams, I don't want you going to places like Chegg or other online resources for the most part, because I want to know what you understand, not what ChatGPT understands or Google can find for you. I want to know what you understand. So what you'll notice about my solutions is that I often talk through my thought process. What am I thinking? How am I looking at this problem? The problem with Chegg and other solutions like that is they typically tell you, okay, do this, then apply this equation, then plug in these numbers, there you go, there's the answer, and you still don't know anything from what you knew before. You don't understand how to think about the problem. You don't understand how to think about real-world problems in order to actually simplify them down to a manageable problem that can be solved. So here's a problem-solving strategy you should get used to, and I will confess on my example problems, I don't really go through this strategy completely. I do read the problem carefully, and I do determine what's given and what needs to be found or returned as an answer. You should ask me if the questions are unclear, especially on tests. But if you have questions on homework or anything, feel free to contact me. If necessary, though, you should make assumptions, but you should indicate what your assumptions are. You should write them down as you're solving a problem. Say, well, I see that this truss is symmetrical. I'm going to assume that loads are symmetrical on each side of the truss. Fine, just tell me. That's all I ask, okay? 2, plan. So think about the major steps. What all will you have to do? Now, I will confess, most students don't like this problem-solving strategy because they don't even know what they're supposed to do. So how can you plan what you're going to do when you don't know what you're supposed to do? There's a lot of validity to that argument. However, try to get an idea of what you think you will need to do before you just say, let me thumb through the book and find an equation, plug in numbers because that seems to fit, and see what happens. Try to think about, well, what's going on in the problem? What, in the real world, what would this be like? How does my intuition think this will go? And how can I apply some of the principles I've learned to this problem? What principles apply to this problem? Now, your task is a little bit easier because if you're working homework in Chapter 4, where are you going to turn for information? Chapter 4, right? That's where the equations are going to be most likely that you need. Now, maybe there's something in a prior chapter that you need to reference, but overall, the problems that are given in the various chapters focus on the content that chapter was supposed to reinforce. So try to think of your strategy, even if you don't know how to get all the way to the end. Try to think through, okay, what would make sense along the way? What could I possibly apply to this problem to get me from the beginning where I don't know the answer to the end where I do know the answer? Think of other ways to solve the problem and just choose whichever path you think is best in order to solve whatever problems I give you, whether it's homework or exams or whatever the case may be. And then finally, carry them out. Use good diagrams. I found one thing that really helps me when I'm solving a problem, even if I have a diagram already, even if I'm sitting there looking at something, it helps to make a simplified diagram of the physical situation in order to, begin processing it in my head and begin to make simplifying assumptions. And that can be very difficult in statics. Making simplifying assumptions is something that takes a little bit of getting used to, a little bit of experience to do. But anyway, estimate your answers, avoid mistakes, and then reflect on your work and revise it if necessary. A lot of times in this class, there's a way to check your work. There's an extra equation floating around that you can use that should balance out. And if it doesn't, you've made a mistake somewhere.